Hello and welcome to the live coverage of the Hera planetary defense mission as it takes off from Earth and chases down an asteroid. I'm Matt Russell and I'm stood in the heart of the European Spacecraft Operations Centre, the main control room. We're really close to the first milestone, so I'm going to hand over to my co-host and legend and personal hero, Andrea Akamatsu. Take it away, Andrea.
Thanks, Matt. Thanks, Matt. Welcome, everybody, to Mission Control. We have the spacecraft sitting on the launcher, and we are preparing for the final countdown here on our side. Flight Director Ignacio Tanco will start now the roll call.
Okay, on the stations. This is OD in the briefing loop. Upon my request, please respond with your call sign, followed by your status go or no go. OM.
OM go.
SOM.
SOM go.
System 1.
System 1 go.
System 2.
System 2 go.
System 3.
System 3 go.
System 4.
System 4 go.
Flight Dynamics.
Flight Dynamics go.
Softcore.
Softcore go.
Software Support.
Software Support go.
Project Rep. Project Support.
Project Support go.
S-Track.
S-Track go.
Scheduling.
Scheduling go.
Okay, this concludes the roll call for Hera. ESOC is go for launch of the Hera mission.
We have just heard Flight Director Ignacio Tanco confirming with all the team leads of his team that ground segment mission control is ready for launch. This is the time where the flight director, acting as an orchestra director, makes sure that all the teams, all his players are ready to go. Each of them knows exactly what to do at any time in the sequence. Now let me check with him. Was it a good roll call? Everybody on the right loop this time, or the usual traditional screw up?
No, I think we got everybody on the right channel this time.
Good, already we start with a very good sign. All the best.
Thank you.
Back to you then.
Thank you so much, and absolutely thank you so much for allowing me to be in this hollowed hall for roll call. It was absolutely amazing. So this is the main control room. I won't be in here, so I'm going to have to leave. But before we leave, let's have just a quick look at some of the iconic flights that have come from here. Some of my favourites. Let's see if you can spot any of your own. I've got Giotto, Rosetta, Huygens, Venus Express, Juice, Euclid. Right, so I think that's probably about enough. I'm probably going to get kicked out. So I'm going to take you to my studio, which is down the corridor. It's just down here. The Spacecraft Operations Centre isn't just a place where they control the spacecraft. It is also a watchtower for planetary defence, and we're going to be talking about that a lot, but it's about solar storms and asteroids and things like that. So I'm going to make my way to my little studio here in the dedicated control room, the astronomy dedicated control room, where they actually fly the spacecraft. So welcome to the astronomy control room. Behind me, you may actually see people coming in and out and controlling European Space Agency's fleet of space telescopes. It's a real working environment, so you might hear some alarms, Star Trek noises, bleeps throughout the show. So at various points, we will switch over to the live feed from SpaceX, and there it is. We can see Hera on the Cape, across the ocean. Pretty cloudy there. We're not including an astronaut who will share their thoughts on space exploration, the incredible value of missions like Hera. Also be getting live updates from Andrea at critical phases during Hera's journey from launch to separation and that really important first signal. So stay with us as we take you through this incredible mission. So joining me now is Professor Alan Fitzsimmons, a key voice in Asteroid. Real quick one with you here, where you're going to tell me how on earth did you even start to conceive of the Hera mission?
Well, it was 20 years ago that the European Space Agency put together a panel of experts, astronomers like myself and space scientists, to look at how ESA could really provide support to planetary defence. And the mission concept we focused on was a kinetic impactor, where you would use one spacecraft to hit a small asteroid at very high velocity and move it move it to a different trajectory, and then a second spacecraft would measure exactly the effects, so you could apply that lessons to other asteroids. And now today we have the NASA DART spacecraft, which has already successfully hit Dimorphos, and now we have Hera on the launch pad to go and make those vital measurements.
Yeah, so what kind of milestones are we looking for today for today for this mission?
Well, we want to get on off the launch pad, and we want to see that acquisition of signal at the end, where Hera calls home and says, "It's okay, I'm on my way to Dimorphos."
Yeah, it's no exaggeration, is it, to say that acquisition of signal is the key moment, isn't it?
Absolutely.
Well, thank you so much, Alan. It's been an absolute pleasure to talk to you. So obviously we're going to get you back later on in the show. So up next, we have a fascinating video that takes you behind the scenes of the Hera mission, from the initial planning stages to the international teamwork, a team of young, lean innovators that are required to get Hera off the ground. This video will give you an inside look at what it takes to make a planetary defence a reality.
"20 years ago, scientists didn't know what asteroids were. Actually, asteroids were not very popular in the science community, so we had very little knowledge about these bodies. There was a very interesting moment in history in 1994 when humankind saw almost live the impact of a comet on a planet called Jupiter. And that's when scientists realized that we could be next. The Hera project actually started almost 20 years ago. A proposal came from a professor called Milani, who proposed a mission called Don Quixote. And the idea was really to interact with the asteroid and trying to deflect it. So sending a spacecraft at very high velocity to impact it and change its orbit, its trajectory, and then sending a second spacecraft to study the outcome of the impact. So the Hera mission took a long time to get funding and being approved. But once it got approved, we only had 4 years to meet our launch window. And to do that, we really needed to do it in a completely different approach.
So in Hera, we work differently to the normal ESA project. The schedule is very compressed, so we have to work in a much more cooperation and close loop with the industry. So we are down to having tests done with equipment in the office to provide quick feedback and customer perspective on how things work. In Hera, we are using existing technology as much as possible, but some customization and new development are needed. An example is this radio system that starts from what has been developed for Proba 3 mission, where only 2 satellites are involved. So in Hera, we had to extend it to be able to handle the 3rd satellite, so having multiple links in parallel running, and to cope with much higher distances compared to the Proba 3. In Hera, we have 2 CubeSats and a mothercraft. The CubeSats are too small to have resources to be able to communicate directly to Earth, so they will rely on Hera to communicate at a short distance at the asteroid, and then Hera, with another powerful system, will communicate directly to Earth, and also the way back.
On board Hera, we have 2 CubeSats called Juventus and Milani. The CubeSat size is presented by this model. So you can see that it's quite small. It's, I would say, shoebox size. So Juventus has radar on board, so that will make first measurements from the distance of the surface of the asteroid. And that gives information to the scientist of the composition of the asteroid. Secondly, there will be images, so they will take images of the asteroid to have the surface, if it's rough, if it's smooth, what kind of a surface is on them.
ESA had a very specific knowledge in building fast and reliable spacecraft coming from the technology demonstration program and the PROGRA satellites, where ESA has worked hand in hand with industry to develop innovative and small satellites. By studying Didymos, the primary body, we can also understand how the moon was formed. The formation processes of these systems is still unknown today. So by studying the internal structure of these bodies, how Dimorphos has reacted to the impact, we can actually improve our knowledge of the formation of the solar system.
So now joining me is Paolo Martino, lead system engineer for the Hera mission. Welcome to the studio. So Hera's not just going on a journey to space today. The spacecraft has actually been absolutely everywhere, all round everywhere. So are you able to talk us through, I believe we've got a video of what's known as the launch campaign.
Yeah, that's correct. As Ian, Haley and Paolo were mentioning, Hera had to be developed at an astonishing high speed, only 4 years to develop a deep space mission. And so we had to take a series of tricks to save time. The spacecraft was built with 2 halves in parallel. This is not common, it's something typically do for telecommunication satellites. Half of it, the propulsion module, was built in Italy at the premises of Avio. The other half, the core module carrying the payloads and the avionics, was integrated in Bremen. Those 2 were mated in last summer, and that's where the spacecraft was born, we can say. And after that, we went to the traditional testing campaign. So we went to mechanical test to check that we could withstand the environment of the launch, thermal vacuum to check that we could actually survive the environment of space, a vacuum, extremely hot, extremely cold. And last but not least, which is one of the most interesting part, is the EMC, electromagnetic compatibility. So as mentioned, we are carrying 2 CubeSat, 2 small satellites that will communicate with the mothercraft via an inter-satellite link. This is because the CubeSat alone don't have enough power, don't have the voice strong enough to talk back to Earth. So Hera will communicate with them and will relay this information to ground, making use of its big 1.1 meter antenna and its powerful amplifiers. This is one of the first time that this kind of approach is used. We are really curious about that, and that was a very breathtaking moment of testing. After that, the spacecraft was packed, the solar wings were installed for one last time, and it was shipped to the US, where with an Antonov it landed on the shuttle landing facility already, a very emotional moment on its own.
Oh, I bet, I absolutely bet. And of course, now it's sitting on top of a Falcon 9. So thank you so much, Paolo. I know it means a lot to you and a lot of insights. I can see you holding in the emotions there. It's hard work all round, isn't it? It's such a hard work to get a mission like this off the ground. So now let's turn our attention to the SpaceX Falcon 9 rockets, marking a really critical step in planetary defence. So let's take a closer look at the Falcon 9 as we gear up for launch. It's beautiful. Very good spacecraft. So let's shift our focus to why this mission is so important. Hera's destination, the Didymos asteroid system, and asteroids in general actually are key to understanding how we can protect Earth from these potential threats. So joining me now is Dora Föring, an expert in asteroid observation and planetary defence. Dora's been deeply involved in the efforts to track and understand near-Earth objects and works at the Near-Earth Object Coordination Centre, the main centre of planetary defence office of the European Space Agency. Welcome to the broadcast, Dora. First questions first. Give us a little bit of background of where the asteroids came from, what are they, and why are they so important when it comes to talking about planetary defence?
Yeah. So asteroids are the small rocky fragments that have been left over from the formation of the solar system. So they're made of the same material that the planets are, but they're just the little bits that haven't made it into the planets. We find most of them orbiting between the orbits of Mars and Jupiter, so slightly further out of the solar system. But they're very important to study because there's quite a large number of them that actually come much closer to the Sun and hence the Earth. And these orbits then can occasionally intersect with that of the Earth and in fact hit us.
Yeah, so you work for the NEO Coordination Centre. What are the sort of, how do you kind of list your kind of priorities that you have there, the sort of pillars?
Okay, so the pillars of the NEO Coordination Centre, the first one that I'm working on is observation. So we're responsible partly for detecting and discovering new NEOs that we haven't seen before, but primarily to follow up objects, so refine their orbits, especially when there's been a new one discovered that we're not really sure of how its orbit actually looks like, to make sure that it's safe and that the orbit doesn't cross that of the Earth. But if there is something that looks like it could be on a collision course with the Earth, to keep refining the orbits and send more positions to the next pillar, which is the orbit determination pillar. So these are mathematicians, and we're constantly calculating and updating the orbits of all the known NEOs. And there's an interplay between the mathematicians and the astronomers, so they can send alerts if they see an object that looks like it's hitting the Earth, and then we can start observing that more rigorously. And then the final pillar is the mitigation, and this is what Hera is part of. So this is, if there is a threat, then what can we do about it? Partly how we communicate the threat without worrying people, but also collaborating with international organizations to launch these fantastic programs like Hera.
Yeah, I'm going to have to stop you there, Dora, because thanks so much for those insights. It turns out that SpaceX have opened up their feed earlier, so we're going to go over to the SpaceX feed now.
Humanity can change the motion of an asteroid in space. DART collided into a small asteroid moonlet called Dimorphos, which orbits around a larger asteroid called Didymos.
Spacecraft is on internal power.
And that happened in September of 2022, about 11 million kilometers or 6.8 million miles from Earth. The collision shortened Dimorphos' orbit by 32 minutes, or about 26 times the predefined success threshold of 73 seconds. Hera will now return to the same binary asteroid system to survey the results of the kinetic impact up close and help researchers understand if it can become a repeatable technique among other mission objectives. Now, before we get into today's mission, here's a quick refresher on the DART mission courtesy of NASA.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
4, 3, 2, 1. For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
DART changed the orbit of a celestial body for the first time in human history, demonstrating one possible capability to defend Earth from a potential future impact. Hera will visit Dimorphos to measure its mass and makeup, as well as its shifted orbit from up close, performing its own crash scene investigation of the asteroid moon. The data gathered will help validate the DART-style deflection technique for operational use in case it's ever needed to help deflect any dangerous asteroids headed for Earth. Hera is the first planetary defense mission for ESA and will be the first mission ever to perform a subsurface radar survey of an asteroid using the smallest radar instrument ever flown in space. To help complete its mission, Hera is carrying 2 shoebox-sized CubeSats with it, one called Milani and the other called Juventus. Milani was named after the late Italian academic who devised the DART and Hera missions, and Juventus is the Roman name of the daughter of Hera. Hera will help pave the way for ESA's future interplanetary missions by testing deep space navigation and guidance and inter-satellite communication between the main Hera spacecraft and its CubeSats, which are packed with miniaturized technology and scientific payloads. The CubeSats will conduct proximity operations in the asteroid's extremely low gravity environment, flying lower and closer than Hera. And they will actually end their mission by landing on Dimorphos, which is 170 meters wide, or roughly the size of the Great Pyramid of Giza in Egypt. Hera is expected to arrive at Dimorphos in late 2026 to begin its 6-month investigation, delivering researchers on Earth critical data about future asteroid deflection missions and continue to grow our understanding of asteroid geophysics and build our knowledge about the formation and evolution of the solar system. With that primer, let's take a look at this video from ESA to dive deeper on today's mission and hear a special message from the ESA Director General.
There's a mystery out there in deep space, and solving it will make Earth safer. That's why the European Space Agency's Hera mission is taking shape, to go where one particular spacecraft has gone before. On the 26th of September 2022, at 6.1 kilometers per second, NASA's DART spacecraft crashed into the Dimorphos asteroid. Part of our solar system changed. The impact shrunk the orbit of the Great Pyramid-sized Dimorphos around its parent asteroid, the mountain-sized Didymos. It also sent a plume of debris thousands of kilometers across space. This grand experiment was performed to prove we could defend Earth against an incoming asteroid by striking it with a spacecraft to deflect it. DART succeeded, but that still leaves many things scientists don't know. What is the crater left by DART's collision? Or has Dimorphos completely cracked apart, held together by its own weak gravity? That's why we're going back with ESA's Hera mission. But Hera is not going alone. It takes with it 2 briefcase-sized CubeSats to go in closer and take more risks than their parent spacecraft. And they'll end their duties by touching down on Dimorphos to gather extra data on its surface and gravity field. If a body of this size ever struck Earth, it could destroy a whole city.
I'm delighted you can join us today to watch the launch of the European Space Agency's Hera spacecraft on board a SpaceX Falcon9 rocket. The risk of an asteroid hitting our planet affects everyone, everywhere, making planetary defense an inherently international endeavor. Hera is Europe's first planetary defense mission, which, together with NASA's DART mission, is part of the International Asteroid Impact and Deflection Assessment collaboration. In 2022, DART demonstrated that humankind is capable of redirecting an asteroid. The mission to Dimorphos and Didymos hit the smaller body and changed its orbit around the larger asteroid. Now, ESA's Hera will visit this asteroid pair to investigate how DART affected Dimorphos. Hera will gather the data we need to turn kinetic impact into a well-understood and repeatable technique on which all of us may rely one day. My thanks go to everyone who worked so hard for so long to make Hera possible. Best wishes for a successful start of this epic journey.
Launching Hera today is Falcon9, a 2-stage rocket developed and manufactured by SpaceX, known for its safe, reliable, and cost-effective access to space. Starting at the top of the vehicle is the payload fairing, a protective shell that encases the payload being sent to space. That fairing will separate and jettison away from the vehicle, exposing the payload once Falcon 9 reaches space. And here you can see on your screen a photo of Hera being encapsulated in that fairing just a few days ago. The fairing halves that we are using today have supported multiple missions, one having flown 12 missions and the other 18. Now, continuing down the vehicle, we have the second stage. The second stage is powered by a single Merlin vacuum engine, or what we call the MVAC engine, which is optimized to perform in the vacuum of space. And below that is the first stage, which contains 8 engines arranged around one center engine held in place by a structure called the Octaweb. Now, each of these Merlin 1D engines delivers about 190,000 pounds of thrust at sea level, which gives Falcon 9 a combined 1.7 million pounds of thrust. The booster supporting today's mission previously launched 22 missions, including Crew 1 and Crew 2, SXM-8, CRS-23, XP, Transporter 4 and 5, Global Star FM-15, ISS Aero C-3, Korea 425, Maxar-1, ASBM, and 10 Starlink missions. Now, due to the additional performance required to deliver today's payload to an interplanetary transfer orbit, this will be the 23rd and final launch for this booster, and recovery is not planned. However, we will be recovering the fairing halves. So with that, let's check in with John I for a status update on today's launch.
The launch vehicle and spacecraft are in good health. They're ready for launch as we are just beyond T-minus 9 minutes to liftoff. The Falcon 9 team reported on console at T-minus 2 hours and 15 minutes. They began their final checks of the launch vehicle and ground systems. We did a final checkout of the flight termination system. That was at T-minus 1 hour and 45 minutes. We then had the Falcon 9 team complete their data review of first and second stage propellant checkouts, as well as the avionics team and the guidance, nav, and control team. And they did all their final data reviews at T-minus 1 hour. At that point, the chief engineer conducted a technical readiness poll, and everything was go to continue. We've also completed at T-minus 38 minutes the poll to proceed with propellant load and launch. And most recently, you might have heard over the countdown net, the spacecraft has gone on internal power at T-minus 18 minutes and 30 seconds. Now, currently, the team at Cape Canaveral Space Force Station, they are loading propellant. That began on time at T-minus 35 minutes when our launch auto sequence began. We're loading 2 propellants on Falcon 9 today, a fuel and an oxidizer. Now, for Falcon 9, our fuel is a refined form of kerosene known as RP1. To burn that fuel, we need a source of oxygen, which we call the oxidizer. Now, most burning that you're familiar with on Earth uses oxygen that makes up about 21% of the air you breathe. But in space, there's no atmosphere to provide oxygen or other oxygen-bearing molecules, so rockets need to carry their own. Now, Falcon 9's oxidizer is super chilled liquid oxygen, what we call densified LOX. Now, the liquid oxygen is chilled well below its boiling point. That allows its density to be increased, and that in turn allows us to load more into the first and second stage LOX tanks. And that's an important advantage for missions like today's, where we need as much propellant as we can carry to get to the required interplanetary transfer orbit. Now, currently on the Falcon 9, you see on your screens, fuel loading is complete on the second stage. We're continuing on the first stage up until about T-minus 6 minutes when fuel loading will wrap up on that stage. And we are loading liquid oxygen onto both the first and second stages right now. In addition to its propellants, Falcon 9 also needs an ignition source to start burning that fuel and oxidizer. And for that, we use a liquid called TTEB.
Stage 1, RP1 load is complete.
And there we're on time. Fuel load on the first stage is complete. I mentioned TTEB. That's an acronym for a mouthful called triethyl aluminum and triethyl borane. Now, when we ignite the engines, we first flow liquid oxygen and TTEB into the gas generator in the main combustion chambers. The TTEB will burst into flames in the presence of the oxygen. So once we have that ignition, the RP1 kerosene fuel is introduced and the Merlin engine goes to full power. And at liftoff, Falcon 9's 2 stages that you can see next to the strung back, they will combine to hold over 1.1 million pounds of the fuel and oxidizer propellants. Now, to provide maximum performance for the Hera mission, Booster 1061 will use all of its propellant. We won't save any for the landing of the first stage. On the weather front, you can see on the screen, it's cloudy, it's been a little rainy. We started the day with a 50% probability of violating launch weather constraints. But the good news is that the weather officer forecasts that we should be go 5 minutes from now. Mostly we've been watching thick clouds, make sure they're not too cold, where you might have triggered lightning. The good news is the clouds are warm. Everything looks just pretty much gloomy, a little rainy.
Tanks are pressing
with
for
that,
strong back retract.
You hear the tanks are pressing. We're getting ready for strong back retract. So inside T-minus 5 minutes, all systems are go for launch from Space Launch Complex 40 in Florida. So Jesse, let's head back and watch the last of the countdown.
Thanks, John. It is T-minus 4 minutes and 38 seconds and counting. And as John mentioned, everything continues to look go for liftoff at T0. Now,
strong back retract has started.
Perfect timing. You heard that call out that strong back retract has begun. Now what's going to happen here is the clamp arms, which are just below the fairing, are going to open up, and once those are fully open, then that strong back, or what we call the TE, or transporter erector, will begin to retract away from the vehicle. And you can see on your screen that those clamp arms are opening up there. Now, the TE is designed to transport, raise, and support Falcon 9 at the launch pad using umbilicals or flexible lines to route the vehicle's fluids, power, and telemetry from the ground systems to the rocket and the payload until Falcon 9 switches to internal power and clears the pad. And you can see the clamp arms are now fully open, and that strong back, there you can see it on your screen, the TE is now moving slowly away from the vehicle. Now this is going to recline just a few degrees here, but at T0 it's going to move even further away, about 45 degrees away from the vehicle as Falcon 9 lifts off. And there you can see that the TE is pretty much fully reclined there on your screen.
We're coming up on T-minus 3 minutes. Strong back is in the countdown configuration. It's about 1.5 degrees away from the Falcon 9. Waiting for next is completion of liquid oxygen loading on the first
Stage 1 LOX load is complete.
Right on time. So at this point in the countdown, the first and second stages are nearly fully loaded with the 1.1 million pounds of fuel and liquid oxygen. We have loaded all of the fuel on first and second stage. Liquid oxygen is now complete on the first stage. The last major event will be T-minus 2 minutes when we finish loading liquid oxygen on the second stage. And you can see right there the cold, chilled skin of the second stage. There's the warm Florida air moving by it. We're seeing the condensation of the moisture in the air. Everything continuing to look good as we come up on T-minus 2 minutes.
Stage 2 LOX load is complete.
And there's that call out that liquid oxygen loading is now complete on the second stage. Now that means that propellant loading is complete on Falcon 9. And that's over 1.1 million pounds of propellants now loaded on the vehicle. All systems remain go for launch. SpaceX ground computers are now draining propellant out of the lines that go up to the strong back onto the second stage, and there you can see that venting happening there on your screen. Now this creates a white cloud, which is pressure from the ultra cold liquid oxygen line that's being vented there.
Front gas closeouts.
And again, when that cold liquid oxygen gas meets the warmer ambient air there, it creates that condensation that you can see there on your screen. Now, the first and second stage computers on Falcon 9 will execute stored programs to prepare the rocket for flight, leading to the ignition of the M1D engines at T-minus 2 seconds and liftoff at T-minus 0.
Falcon 9 is in startup.
With that call out, the Falcon computers are running the final sequence for launch. First and second stage tanks are beginning final pressurization for launch. All systems are go. Let's listen into terminal count.
LD, go for launch.
As Falcon 9 transports the European Space Agency's Hera spacecraft into space.
30 seconds. 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition, engines full power, and liftoff. Go Hera, go Falcon, go SpaceX. Vehicle is pitching downrange. Stage 1 propulsion is nominal.
At T plus 30 seconds and counting, Falcon 9 has successfully lifted off from Slick 40. After clearing the tower, we begin to tilt or gimbal the engines. That initiates a roll maneuver you might see on the Stage 1 camera view, although it's kind of cloudy. But this enables the vehicle's antennas to stay in the best position for communicating with the ground. We are into throttle down now in preparation for max dynamic aero.
Falcon is supersonic.
Faster than a speeding bullet, we're supersonic on Falcon 9. Waiting for the call out from GNC of Max Q.
Max Q.
Right on time. We're through the period of maximum pressure on the vehicle. The Merlin engines are back at power, and we're out of the throttle bucket. Now, from here on, even though the velocity is rapidly increasing, the atmospheric density is decreasing, and that's resulting on less loads on the Falcon 9. 90 seconds into flight, the rocket typically needs to go 17,500 miles per hour horizontally in order to avoid gravity pulling it back down to Earth and getting into orbit. We've heard the call out for MVAC chill. That's a bleed valve on the second stage engine that's performing the final chill prior to second stage engine ignition. All's looking good with the first stage trajectory. We're coming up on T plus 2 minutes. Views from onboard the camera mounted on the inner stage of Booster 1061. Now we've got 3 events that'll be coming up in just under 30 seconds. Main engine cutoff, the 9 Merlin engines will be throttled down and shut down. Then we'll get stage separation and then startup of the MVAC engine on its first of 2 burns on the second stage. We've begun throttling down the Merlin engines.
Main engine cutoff.
Call for MECO.
Stage separation.
Successful stage separation.
MVAC ignition.
MVAC ignition and we're up on power on stage 2. Coming up will be fairing deployment. And for the first stage, as we saw it in the background, farewell 1061, and we thank you. As we continue climbing out of Earth's atmosphere, we're waiting for the right time when we can open up and deploy the fairing. That should be coming up in about 10 seconds. There's a camera view as we switch. You can see Hera inside the 2 halves of the fairing.
Fairing separation.
And successful payload fairing separation. As we mentioned,
trajectory.
They'll deploy and they'll be recovered by our recovery vessel, Doug. Jesse, T plus 4 minutes, 23 seconds. Everything continues to look good on Falcon 9 with Hera.
Thanks, John. Yeah, everything's looking great. We got some awesome views here on your screen. What you're looking at is a view of the MVAC engine on the second stage with a beautiful view of Earth in the background.
STS has safed.
Now, we are currently in the first of 2 planned MVAC burns for this spacecraft. And we have separated for the first stage from the first stage. As we mentioned earlier, we will not be recovering the booster as we usually do. Now, typically we would land the booster either on a drone ship or back on land, but due to the performance, the additional performance required to deliver this payload to an interplanetary transfer orbit, we will be not recovering the booster today. Now what you are seeing, again, is the MVAC engine. The MVAC engine is optimized for the vacuum of space and has about 220,000 pounds of thrust in vacuum. Again, this is the first of 2 burns. The 2 burns for the MVAC engine will take the second stage with the payload attached to the targeted drop-off orbit.
Falcon continues to follow a nominal trajectory.
And great call out there, following a nominal trajectory. You can also follow along with the speed of the vehicle as well as the altitude in the bottom right-hand corner of the screen. And the next event coming up in about a minute and a half from now is SECO 1. SECO 1 is second stage engine cutoff 1, which is where we will shut down that MVAC engine and allow the vehicle to coast with the payload in an Earth orbit, and then we'll reignite that MVAC engine for a second time to take the vehicle and payload to that interplanetary transfer orbit. Now we're just about a minute away from SECO 1. And you can see in the bottom right hand of your screen that the speed is continuing to pick up. The velocity is increasing on the vehicle as the MVAC engine continues to burn. But again, in about 40 seconds from now.
Stage 2 is in terminal guidance.
In about 35 seconds from now, we will shut down that MVAC engine and again allow the vehicle to coast in an Earth orbit before we make its way to the interplanetary transfer orbit.
Stage 2, SDS says safe.
Continuing to get good callouts and some great views here. Again, this is from the second stage looking at the MVAC engine. The Hera payload is still attached.
MVAC shut down.
Nominal park orbit insertion.
And great news, we heard the callouts as well as saw that MVAC engine shut down, and we got a good confirmation of nominal orbital insertion. Now the second stage is now embarking on the first portion of its coast phase. Coasting in this orbit will last about 45 minutes, and we will light that MVAC engine for a second time around T plus 52 minutes. So we're going to take a pause, and we'll see you back here at T plus 52 minutes for SES-2.
Groundbreaking mission, literally.
A year ago today, the world watched as the DART spacecraft smashed into moonlit asteroid Dimorphos with the goal of changing its orbit. This kinetic impactor test was NASA and the world's first planetary defense test. Our momentum didn't end with DART's collision. Here's what's happened in the last year. In the immediate moments after impact, telescopes from around the world captured a burst of bright light, and the Italian Space Agency's LICIACube made its flyby. DART scientists were looking for the amount of ejecta, the plume of debris generated by the impact that would give Dimorphos an extra push. Turns out, it was a lot, ultimately moving Dimorphos more than the spacecraft itself. When the math was done, the orbit change was a whopping 33 minutes. While analysis is ongoing, knowing this crucial number confirms that a kinetic impactor is a viable solution and will help scientists calculate how far in advance future missions may need to deploy. The ejected tail would eventually stretch to over 70,000 kilometers long, about 10,000 tons of debris, and is still visible when last observed over 9 months post-impact. This ejected material are not on a course to be a threat to the Earth, but tracking them provides a better understanding of this unique test. The stunning images sent down by the Draco camera before impact have gotten a helpful lighting boost from the reflection off of Didymos, what the team is calling Diddy Shine. Modeling work using these images have allowed the team to build out the precise geography of Dimorphos, including the exact collision site. This work will be supplemented in 2024 when the European Space Agency Hera launches. Hera and its CubeSats will arrive in 2026 and land on the asteroid system in 2027 and provide radar imaging that can tell us more about the impact and about Dimorphos itself. The more we know about Dimorphos's specific traits and makeup, the better that scientists can extrapolate how kinetic impactors can affect other asteroids that we may one day discover heading our way. DART was the first ever planetary defense test for the world. The lessons learned in the days and months since impact have put us in a better position than ever before to defend ourselves from
achievements. Someone at the forefront of planetary defence is Lindley Johnson, and he's head of planetary defence, no less, at NASA. He was unable to join us in person today, as he's probably going to be at the Cape for the launch, but he has prepared a special video for us, and it explains DART's heritage and how the European Space Agency, with the Hera mission, is building on that legacy to take planetary defence to the next level. So let's take a look.
Hello, this is Lindley Johnson from NASA's Planetary Defense Coordination Office. We want to give our congratulations.
Look into the NASA and ESA collaboration. Now, I'm actually really excited about this. What's really exciting about the Hera mission is that we're not just talking about one spacecraft. It's actually carrying three. Well, there's three. It's carrying two. Hera is carrying two CubeSats on board, each with its own specific mission to gather even more detailed data from the asteroid. To tell us more about these incredible mini spacecraft, let's take a moment to explore the world of CubeSats. So joining me now is Filippo Corradino, the Chief Technology Officer of Tyvak International, the company behind one of these innovative CubeSats that are on board the Hera mission. Filippo, welcome to this little studio of ours.
Thank you. Thank you.
So we just heard there that there was this impact crater and the Hera mission is there to kind of investigate what's happened to that asteroid. So why CubeSats? Why do we need CubeSats to help?
Sure. Well, CubeSats are very small, the size of a shoebox, and they can be released, these two CubeSats, by Hera, a few kilometers out from the asteroid. And their mission is to take more risks than Hera can by itself and get as close as possible to the asteroid and bring their instruments really where they can do the most. And in the end, actually even land on the asteroid, which would be a first for CubeSats.
I mean,
ever.
Yeah, I mean, it's always great to have a first on a mission, and that's certainly a pretty cool one.
Pretty cool, yeah.
It's a very good one. So each of the CubeSats on board Hera has its own unique mission.
Yes.
So can you tell us a little bit about each one and what they're designed to do?
Yes. Well, Juventus will look more at the structure of the objects. So it's got this radar, and by listening to the pings and echoes of the radio waves passing through the asteroid, can tell us whether it's a solid chunk of rock or if it's a rubble pile, so many different rocks just held together by gravity. And once landed, can also measure the surface gravity with another instrument. While Milani is more of a little chemist, let's say, it will look at the composition of the asteroid. So we've got a camera with visible light and infrared light sensors, and can tell us if which minerals are on the surface, if there's water, how much of it. And we also have got a dust detector. We expect after the impact there will be a lot of dust in the environment, and we can measure how much of it is there, and what it's composed of.
Yeah, so the naming of the CubeSats. So at first glance, you might think it's football related with Juventus and Milani. So, but I'm told that that's not the case.
No, it's just a coincidence, actually. So Juventus comes from mythology. It's the Roman name of one of the daughters of Hera, the goddess. While Milani is named after Professor Andrea Milani, who was the first astronomer who had this idea of the double mission with the spacecraft to impact on an asteroid to deflect it, and another one to go and run this crime scene investigation, check the aftermath, what's happened, and do the science.
Yeah, I mean, I really love the fact that it's Milani. It's such a fitting tribute to the man himself, whose idea that we're really kind of looking at. And I just love the fact that you're using CubeSats. It seems that CubeSats have sort of really opened up that space exploration to many more people and many more institutions.
Absolutely, yes. It's very, very nice, very interesting missions.
So, yeah. So the mission is full of firsts. So can you tell us, is there any sort of new technologies or groundbreaking technologies that are on these CubeSats?
Well, sure. For instance, on Milani, we had to develop a new thruster to move around the system, so a cold gas thruster, which needed to be very tiny because they're small, so they're packed full of equipment. And so we had to develop from another existing one a smaller, more compact thruster, and it's got these little tiny jets, very, very tiny jets to move around, and many other innovations, navigation cameras, radios also, the link with the mothercraft, the intersatellite link. It's a new piece of equipment.
Yeah, so that was something we saw earlier on. Was that tested in that big room with the big
Yeah, that was the
triangles?
Final test for the ISL, with all the spacecraft communicating with each other and with the ground in that moment.
Yeah, were you there at STech when that was
I was not. A colleague of mine that was there, yes, but it was very exciting. It was remotely dated.
As an old acoustician, that's one of my favourite rooms I've ever been in.
It's huge.
It's such a good little space. So yeah, they talk to Hera and then Hera talks to Earth. Have I gotten that right?
Yes, absolutely, yes. Because you cannot feed the radios you need to communicate directly with Earth on these tiny boxes.
Yeah, I mean, it's brilliant. It's brilliant. CubeSats going out into deep space and landing on asteroids. You couldn't make it up. So thank you so much, Filippo, for joining me. It's fascinating insight into the role of CubeSats these days in missions like this. So it's incredible to see how much innovation is packed in. So now just a quick reminder why we're all here today. This is a major moment in planetary defence as ESA's Hera mission builds on the legacy of DART, taking us one step closer to understanding how to protect the Earth from asteroid threats. We're now checking out the SpaceX feed as the launch vehicle approaches its long coast phase. This is a critical part of the mission, with the vehicle cruising through space before the next major event. The team is closely monitoring everything as we move towards the next phase of Hera's journey. So now we've had a glimpse at the spacecraft progress, it's a great time to look ahead to the future of planetary defence. Here is just really the beginning. The follow-up mission will be Ramses, and that will build on the knowledge that Hera gathers this time round and push the boundaries even further. So I'm really pleased to bring back Paolo Martino, lead system engineer for the Hera mission, who will share more about both Hera and what we can expect from the exciting Ramses mission. So welcome, Paolo. Once again,
thank you.
How's your emotions?
Luckily, I had some minutes to recover because it was really a very emotional moment. I just run out of tears. That's good.
You've run out of tears, right? That's fantastic. So,
changing the spacecraft trajectory and those bringing huge fuel savings on the mission.
I think we've got on the screen behind us the actual orbital maneuvers.
So this animation is for the trajectory the planned trajectory we will be flying as of today. Here we're going counter Mars, which, by the way, will also take the opportunity to fly by one of its moons, Deimos. As said, the passing close by Mars gives us a gravitational kick. Then we perform another maneuver in deep space, which targets the encounter with the Didymos asteroid system. And then we start the rendezvous phase, in which we perform a sequence of braking maneuvers. As we approach the asteroid, we align the velocity of the spacecraft to one of the asteroids so that we can start the proximity operations.
Yeah, so if we'd missed today's launch window, you'd actually planned another one, which is completely different. So I think we can probably look at that one as well.
So yeah, this would be on the right side. So we have a backup trajectory for 2026. Now we know happily we don't need it. Had we had to use it, it would have two main drawbacks. One is that Mars would be at the wrong location, so we couldn't use its gravity. So this means we would have to spend much more fuel on the spacecraft side. The other one is at launch, the offset in orbit phase between the Earth and the asteroid would be wider, meaning that it cannot catch up in a single orbital revolution around the Sun, so we'll have to spend 2 revolutions, which extends the transfer duration by a bit more than 2 years, which is the orbital period of the asteroid. meaning that we could start proximity operations in early 2031 instead of late 2026, which we hopefully will manage since we managed to launch.
Yeah, absolutely incredible. So it's a good job we did launch. Fantastic. I mean, it always amazes me the trajectories. I don't even know where you start or how you do it. Particularly, oh yeah, we'll just take in one of Mars's moons as well. Job done. So thank you so much, Pablo, for joining me. That's a great explanation. Before we take a short break, let's quickly check.
The incredible adventures of the Hera mission. Asteroid on collision course with Earth. Imagine the headlines. It may sound like science fiction, but to date we've discovered more than 20,000 asteroids whose orbits bring them dangerously close to Earth. It's a hazard the dinosaurs were powerless to stop. With all the advanced science and technology in our hands, could we do better? Planetary defense requires planetary cooperation. Meet the Hera mission, led by the European Space Agency, set to rendezvous with a binary asteroid system in 2026. Didymos is orbited by a smaller asteroid, Dimorphos. This pair poses us no risk, but our experiments with them will be key to keeping Earth safe. Dimorphos is a small asteroid, yet a rock of its size could devastate a small country or large metropolitan area. Studying asteroids like this from Earth is challenging. As a matter of fact, today we still know very little about their physical properties. The only way to capture their secrets is to go and visit, so we need Hera to get up close and personal. When Hera reaches it, Dimorphos will already have been impacted by NASA's Double Asteroid Redirection Test, or DART for short. This cosmic shove is expected to slightly shift the orbit of the asteroid moon. Hera will examine the crater left by DART, the composition of Dimorphos, map its surface temperature, and probe its internal structure, similarly to an X-ray. Meanwhile, Hera will deploy two briefcase-sized CubeSats called Juventus and Milani. Packed with high-tech equipment such as a low-frequency radar, a mineral mapper, dust analyzer, and a gravimeter, these mini-satellites will get an even closer look before attempting to land. Altogether, the DART impact and Hera's data will let us understand whether this technique can be used in the future to deflect an asteroid on a collision course with Earth, like an astronomical game of billiards. In addition to Hera's main planetary defense quest, the mission will gather invaluable bonus science. New understanding of collision physics and crater creation could revolutionize our understanding about how the solar system was formed. Hera will even test new techniques for autonomous deep space navigation and guidance, while working in the asteroid's extremely low gravity. This will help pave the way for future interplanetary missions. Not bad for a space probe the size of an office desk. Hera, defending Earth, one asteroid at a time. The incredible adventures of the Hera mission.
In 1609, Italian astronomer Galileo Galilei became the first person to use a new invention, the telescope, to look at the moon. He was astounded to find strange circular features. Great minds of the time thought they could be volcanoes, glaciers, or even coral. Fast forward to the 20th century, and scientists had discovered many of these craters throughout our solar system, and even on Earth. They realized the craters must have been formed by explosive impacts.
Space rocks smashing into moons and planets.
Exciting. Studying craters became key for us to learn about the evolution of the solar system. They're like timestamps. The more craters, the older the surface. But there's only so much you can work out without knowing exactly what made a crater. So, we need to create a crater. For this quest, ESA's Hera Asteroid Detective is teaming up with NASA's DART, which is on a collision course with an asteroid called Dimorphos. DART aims to create the solar system's newest and perhaps most important crater. This time, we will know precisely the size, mass, and speed of the crater maker. DART will never actually see the crater it forms, so to unveil its secrets, Hera will take to the stage. Hera will take high-resolution images to chart its size and shape. The collision will blast out material from under the surface of Dimorphos, giving Hera a unique peek into what the asteroid is made of. Analysing this new timestamp will even help us work out how long ago Dimorphos was formed. Hera's discoveries will reveal more about the history and future of our solar system and help us learn how to deflect asteroids away from a collision course with Earth. It all starts with creating a crater.
The incredible adventures of the Hera mission. Imagine you're going on a 2-year journey with no map, and once you arrive, you must conduct cutting-edge science using only what you have on your bag. That's exactly what Hera, ESA's asteroid detective, is going to do. To carry out her mission, she's packed with more gadgets than James Bond. Hera's target is the double asteroid Didymos, and in particular its small moon Dimorphos. The pair are 181 million kilometers away, but each measures just a few hundred meters across. To find Didymos, Hera will use an advanced camera to constantly scan the skies, looking for a single dot moving more than the others against the background of stars. Bingo! The same navigation camera will then be used for science, joining other high-tech kit, including a laser altimeter and thermal camera, mapping Dimorphos' shape, and discovering what it is made of. As it moves closer and closer to Dimorphos, Hera will be largely autonomous, like a self-driving car, tracking down a crater made by NASA's DART mission. Hera has 2 intrepid assistants, also packed with new tech.
The first burn placing Falcon9 and the Hera spacecraft into the desired orbit about 3 minutes ago after launch. Now, we are approaching the second burn of the engine to carry Falcon9 and Hera to the orbit needed to deploy the spacecraft. Now, coming up here in a few seconds should be...
And back ignition.
And right on time, SES-2. That call out was for second stage engine start. Now, this burn is planned to last about 1.5 minutes. And we got a great view of that MVAC engine burning very bright there. Now, during this time, we will be adding 4,500 kilometers per second to our velocity. And again, on the bottom right hand of your screen, you can see the speed increasing rapidly there, and you can also see the altitude of the vehicle and the payload. Now, this is the second burn for this mission. There are 2 planned burns for this payload to be dropped into an interplanetary orbit. So that first burn took us into an Earth orbit, and now this second burn that's currently happening right now is taking the vehicle and the payload to that interplanetary orbit where the Hera spacecraft will be deployed. Now, we're just about 30 seconds away from the conclusion of SES-2, which will be SECO-2, that second stage engine cutoff 2. And then we will shut down that MVAC engine, allow the vehicle to coast for a little bit prior to the deployment of the payload. Now, SECO-2 is coming up here in just a few seconds.
MVAC shutdown.
We did have SECO 2, just waiting for confirmation of a good orbit. There you can see on your screen the MVAC engine has shut down. And the Hera payload there on your screen still attached to Falcon 9. If you're just now joining us, we did have 2 completed burns for that MVAC engine. About a minute ago, we had SECO 2 where that second stage engine did cut off, and you can see that there, no longer firing. And we do still have the Hera payload still attached to Falcon 9.
We were waiting to hear the guidance nav control officer call out a good burn. I think they may have been stepped on. We're looking at the data and we've heard the background chatter. We do have confirmation.
Nominal burn 2.
There we
Good
go.
orbit.
The chief engineer has confirmed we have a good second burn of the MVAC engine. So that means the Falcon 9 second stage, with the Hera payload still attached, has escaped Earth velocity. So we're no longer orbiting the Earth. We're now orbiting the sun. We've got one more major activity remaining in this launch mission, and that's the spacecraft deployment. You can see the Hera spacecraft right there, still attached to Falcon 9 second stage. That's expected to occur at T plus 1 hour and 16 minutes. So we've still got another 20 minutes, which means we're going to take a short break. And we'll see you back here at T plus 1 hour and 15 minutes for spacecraft deployment.
But I mean, Voyager don't even go there. So yeah, it's amazing. So thanks very much for sharing those insights. So now the moment we've all been waiting for, it's just around the corner. Separation is imminent, and Hera is about to begin its own little independent journey into the vast inky blackness of space. We're ready to switch over to the SpaceX feed to witness this thrilling event live as Hera prepares to embark on the incredible mission to the Didymus asteroid system. Let's turn to the feed now.
We were able to get the weather to cooperate. We had a successful ascent, stage separation, deployment of the Hera spacecraft from Falcon 9's second stage. That's going to happen just over 30 seconds from now. And you may have noticed when we shut down the engine at the end of the second burn, we were 204 kilometers, a little more than 120 miles above the Earth. If you look at the display on the bottom right of your screen, we've just crossed 7,400 kilometers as we continue to head out into deep space as we have exceeded the velocity to escape from Earth. But right now, let's listen to hear the call out and watch for separation of Hera from the second stage.
Hera separation confirmed.
Great view. We've got successful deployment of the Hera spacecraft.
And with successful payload deployed, that brings our webcast to a close. Today's mission marks SpaceX's 389th overall mission to date and 94th mission of this year. Thank you to the European Space Agency for entrusting us with today's mission, as well as the range for their support. For continuing coverage of the mission, check out @ESA on X. And for continued updates on all of our missions, follow @SpaceX on X and spacex.com/launches. Thank you to all of our viewers for joining us this morning, and we'll see you again soon.